to this topic. Okay. First of all, why why do we require Laplace transform? What is the need of Laplace transform? There are basically certain limitations in this Fourier transform or Fourier analysis that has forced us to shift to Laplace transform. Okay, so limitations of Fourier transform and need Laplace transform. I'll write a few lines and I'll explain them. So what are the limitations of Fourier transform and why do we require Laplace transform? We should remember that first of all, the Laplace transform, it is just like a mathematical tool. It is a mathematical tool just like Fourier transform. Fourier transform is also a mathematical tool which is used to analyze complex sinusoids. We have already discussed it. Similarly, Laplace transform is also a mathematical tool like Fourier transform. But the advantage here is it provides us a broader characterization of continuous time linear time invariant systems. Okay, तो ये जो है Laplace transform, it is basically generally useful for linear time invariant systems, and it is used in many areas, but in case of linear time invariant systems, it will provide you a broader characterization, a broader picture of the system. Okay, what kind of broader picture? How do these systems interact with various signals and their interaction with signals Okay, so how do LTI systems interact with various signals? It gives us a broader picture. हम इसको आगे देखेंगे what are its uses, but I'm just writing them down. I'll then explain them one by one. Laplace transform can be used to analyze a large class of signals, a large class of continuous time problems involving signals that are not absolutely integrable, that are not absolutely integrable. Now see, one of the most important characteristic feature of Fourier transform is it always involved integration of something, summation of something, integration from minus infinity to plus infinity. In Fourier transform, if you observe the general expression of Fourier transform or Fourier series, you will find there that there will be a summation associated or an integration. So Fourier transform in general, they are used or they are applicable, that kind of mathematical tool is applicable on the signals which is absolutely integrable, which is absolutely summable. It cannot be it cannot operate on those signals which are not absolutely integrable, whereas Laplace transform, it can operate on any signal whether it is integrable absolutely or it is not integrable. So that is why there is a limitation in Fourier transform. It can act only on those signals which are absolutely integrable. Like in Laplace transform, whereas in Laplace transform, it can act on any signal which is absolutely integrable or which is not absolutely integrable. Okay. So what are the examples uh, which are not absolutely integrable signals? Okay. So Laplace transform can be used to analyze a large class of continuous time problems involving signals that are not absolutely integrable. For example, such signals are impulse response of an unstable system. Okay, because we know that Fourier transform does not exist. Fourier transform does not exist for those systems which are not absolutely integrable. Okay, which are not absolutely integrable. Now, we should remember that Laplace transform further it possesses a distinct set of properties to analyze such systems. Which systems which are not absolutely integrable? Many of these properties are although parallel to Fourier transform. Okay, many of these properties are found in Fourier transform also, but some of the properties are not coinciding with Fourier transform. So in general, we say Laplace transform, it comprises, or it comes in the form of two varieties. तो जो Laplace transform जो हम डिस्कस करना चाहते हैं, it exists basically in two different forms. One is known as unilateral Laplace transform, unilateral, or it is also known as one-sided Laplace transform. This unilateral and one-sided Laplace transform, it is a convenient tool. It is a convenient tool which is used for solving differential equations, differential equations with initial conditions, with initial conditions, initial conditions. You must have studied it in your network theory. You know, you have differential equations and you want to solve them using Laplace transform. If you have studied them, they have also initial conditions when the system will be switched on, and at t equal to infinity when there will be transient state. So such kind of examples in Laplace transform, they come in unilateral or one-sided Laplace transform. The second class is known as bilateral, bilateral or two-sided Laplace transform. Okay, bilateral or two-sided Laplace transform. The bilateral Laplace transform, it basically offers insight. It offers insight into the nature of systems, into the nature of system characteristics, such as stability. So bilateral Laplace transform, it is used to determine the stability of the system, whether the system is stable or not, or even it can determine causality of the system, whether it is causal or not, or, uh, or it can define the frequency response of the system. So such type of Laplace examples, they will be covered in bilateral Laplace transform. We'll be discussing them in our coming lectures. Okay. Now, but the primary role of the Laplace transform in engineering, it is the transient and stability analysis. I said that Laplace transform, it is used in various areas of engineering, but the primary role, whether in civil engineering or in mechanical engineering or in any branch of engineering, the primary role of Laplace transform in engineering is transient and stability analysis. So network analysis में you have studied probably the transient analysis of a network, transient analysis of a circuit. Transient analysis would mean analysis or response of a system with time. Transient analysis would mean response of a system with time at t equal to 0 and at t equal to infinity. So the primary role of Laplace transform in engineering is transient and stability analysis of causal linear time invariant systems, okay, which are described by the differential equations. So what is then Laplace transform? Laplace transform. So this was the need and the limitation of Laplace transform. Why do we require it? because it's a very useful tool. There are limitations in Fourier transform which cannot, you know, they cannot analyze those signals which are not absolutely integrable, while as Laplace transform can do it very easily. Okay, so we'll discuss now Laplace transform. What is Laplace transform? I'll let us assume that we have e raised power st, which is basically a complex. When you have something exponential, okay, it means it is a complex, because e raised power iota theta, it can be, you know, represented in the form of cos theta plus j sine theta, something like that. So let e raised power st be a complex exponential with complex frequency s. So s is nothing. What is s? S is the complex frequency. And what is s equal to? S, I am assuming it is a complex frequency, and it is equal to sigma plus j omega. So e raised to power st would mean it is e raised to power sigma plus j omega, which is basically a complex exponential now. Okay, then we may rewrite by exploiting the Euler's formula, Euler's formula. We can write that uh, e raised to power st will be equal to e raised to power sigma plus j omega t. Okay, sigma plus j omega t, and which can be further then simplified as e raised to power sigma t. Then you have e raised to power j omega t inside. Okay, j omega t. So what is theta here? Theta is omega t. So it is, if we try to correlate it, e raised to power j theta, general form, in Euler's equation. So theta will be here omega t. Then we can write down it as e raised to power j omega t will be written as, it can be written as cos theta plus j sine theta. So it is cos theta. What is theta? It is omega t plus j sine theta. What is theta? It is omega t. Okay, it is omega t. Or we can rewrite this equation as e raised to power st will be equal to e raised to power sigma t cos of omega t plus j e raised to power sigma t into sine of omega t. Okay, sine of omega t. Now see, this is a complex exponential signal. This is a complex exponential signal. E raised to power st is a complex exponential, okay, which has some complex frequency also. Now, the real part of this complex exponential, real part, real part, real part is this one, okay? This is the real part. This is the real part. And this one is the imaginary part. This is the imaginary part. Now see, if we try to analyze on the real part, this is imaginary part. If we observe real part carefully, the real part of this signal, which signal? E raised to power st, is nothing but it is an exponential or exponentially damped cosine. Damped cosine. Okay. Now see, we have damped signals, we have undamped signals. Undamped signal. This is undamped signal. See, if this is a signal, and let me draw it somewhere else, or let me draw it here only. See, if this is a signal, its amplitude remains constant with time. Its amplitude remains constant with time. For example, this is your signal. Its amplitude does not change. Okay, its amplitude does not change with time. Its amplitude remains constant with time. That means this signal is not damping down. It is not dying down. This is an example of undamped oscillations. Undamped oscillation. Okay. Similarly, we can have another signal here, which we can think that it goes like this. See, the oscillations were quite high initially, but then finally the amplitude tried to die down. This is known as damped oscillation. This is known as damped oscillation. Okay? This is known as damped oscillation. With time, the amplitude of the signal, it dies down, and finally it will be zero. Okay, finally it will be zero. Now see, if you observe this e raised to power st, real part of e raised to power st is exponentially damped cosine. Exponentially damped cosine. See, in real part, you have two parts. One is cos theta. What will be the result of cos theta? Cos theta का result होगा oscillation. Which type of oscillation? A sinusoidal oscillation, cosine wave. Okay. And what will be the result of e raised to power sigma t? E raised to power sigma t, its result would be uh, damping, damping exponentially. Okay. So I will plot this real part first, and you will understand this thing. See, you have a real part here. Let me draw it here. It will require. This is time. Okay. Since real part is multiplied by cos, और cos theta ऐसा है, ये cos theta है. This is cos theta, and this is sin theta. Sin theta 0 से start होता है. So there is difference in cos theta and sin theta. So if it is multiplied by cos omega t, real part में cos omega t multiply हो रहा है, so it will start from 1. So somewhere here 1. Okay. So say for example it starts from here 1, and then it will go on like this. So this is 1 here. Okay. तो यहाँ से इसका ऐसे होगा. If you will mark its outline, it is exponentially decreasing. This is exponentially damping. So what is this plot? This is plot about real of, or RE, real of e raised for st, real of e raised for st. And this means e raised for minus sigma t, and it can be e raised power plus sigma t, e raised power plus sigma t, and this is time. तो होता है स्टार्ट कहाँ से? cos से. This is starting from cos. रिजवान is here. रिजवान बेटा आप यहाँ हो?
जी सर.
ओके. अफनान को समझ में आया? रोल नंबर 13.
Yes sir.
Okay. Now see about e raised power st, it has another part. So the real part ऐसे plot होगा. Now it has an imaginary part also. Okay. That is e raised power sigma t into sine of omega t. यानी उसमें आप दो सिग्नल्स को मल्टीप्लाई कर रहे हो, एक साइन थीटा और e raised power sigma t. अब जो साइन थीटा है it will also start, but it will start from somewhere 0. अब यहाँ 1 से स्टार्ट हो रहा था, यहाँ 0 से होगा स्टार्ट. Maybe this is imaginary part of e raised power st, e raised power st. So this is also exponentially damping oscillation. This is exponentially damping oscillation, e raised power minus sigma t, and this is e raised power plus sigma t, plus sigma t. We are silent about sigma right now. ठीक है, हम sigma को आगे define करेंगे. So this is how it will look like. The imaginary part will be plotted in this way, and real part will be plotted in this way. So this is real of e raised power st. Okay. Now see, if we assume that we will apply, this is my signal now. Okay, this is e raised power st is a complex exponential signal. If I assume, now see, this signal is comprised of two parts. One is real and imaginary. If I assume now this signal is applied to a linear time invariant system. Okay, it is applied to a linear time invariant system. So I'll consider applying an input of the form x of t equal to e raised to power st to an linear time invariant system with impulse response equal to h of t. Okay, so we have a linear time invariant system. This is linear time invariant system. Its system operator is h. I am applying a signal which is x of t. What is x of t equal to? It is equal to e raised to power st, and I will be obtaining an output from it, y of t. And mathematically, if I will write down, it will be y of t is the output. It will be system operator times x of t. System operator times x of t. Okay, and we know that y of t for a linear time invariant system, if the system operator is if we are taking basically impulse response of this system, linear time invariant system, if we take impulse response, then we know that it is nothing but a convolution. It is nothing but a convolution. Okay, because we are saying that consider applying an input of the form of x of t to a linear time invariant system with impulse response h of t. तो अगर impulse response linear time invariant system का देखेंगे, then it is a convolution. So we can also write then down y of t is nothing but it is impulse response of x of t, of the system with x of t, that is the convolution. And what is the convolution integral? Integral of convolution is integration of minus infinity to plus infinity h of tau x of t minus tau d tau. Okay, now since we know that since our x of t it is equal to e raised to power st, our input signal we are now assuming it is e raised to power st. So what is y of t then? Y of t will be minus infinity to plus infinity h of tau. Then instead of x of t we will write down e raised to power st, e raised to power st, e raised to power
सर
st,
ये e raised power minus st नहीं होना चाहिए
e raised to power st or minus st.
सर e raised power minus st, फिर वहां पे हमें हो जाएगा minus sigma plus j omega जो आपने ऊपर लिया, s is equal to.
Just a second, I'll check. It should be e raised to power minus st. I am also thinking that it should be e raised to power minus st. Just a second, let me check it. I have written e raised to power st. This should be, it should be e raised to power st. ये ठीक है वैसे. I'll just reframe it. Let me write it down. So it should be e raised to power st. E raised to power st. X of t minus tau. हाँ तो ये ऐसे बनेगा s of t minus tau d tau. ठीक है, तो अगर ये ऐसे बनेगा, just a second. So can I write it down like this? Y of t will be equal to integration minus infinity to plus infinity h of tau e raised to power s t into e raised to power minus s tau d tau. Where is the problem now? कहाँ पे आपको कहाँ पे प्रॉब्लम लग रही थी? Who was asking this question?
सर e raised power minus st होता है इसका, जब हम लेते थे ना लैप्लास में कर्नल फंक्शन.
अभी तो मैंने लैप्लास निकाला नहीं, अभी मैंने लैप्लास तो नहीं कहा ना अभी. See, right now I have not discussed the Laplace transform. What is Laplace transform? I'm just taking a signal, I'm giving it to the linear time invariant system. ठीक है, अब मैं उसको एनालाइज कर रहा हूँ. मैंने जनरल फॉर्म अभी नहीं निकाली लैप्लास की. दिस इज नॉट द कंक्लूजन नाउ. ठीक है, so right now what I have done, I have given a signal, an arbitrary signal which is a complex exponential with certain complex frequency. एंड आई एम अप्लाइंग टू a linear time invariant system. ठीक है, अब मैं उसको देख रहा हूँ कि what is the response. See, this is my signal, e raised to power st. So I don't think I'm making a mistake, but still I'll try to see whether I'll be able to conclude it. But till now, I think I'm going in a good direction. This is not Laplace transform right now, which I have derived. अभी तो वो निकला नहीं है. So when once I'll derive it, then I'll tell you. So I have now this thing. Okay, this y of t will be equal to minus integration minus infinity to plus infinity h of tau e raised to power st into e raised to power minus s tau d tau. Okay. Then I can write down y of t will be equal to, see, I am integrating with respect to tau. I am integrating with respect to tau. Then e raised to power st will be constant. E raised to power st will be constant. So I'll be left inside integration minus infinity to plus infinity h of tau and e raised to power minus s tau d tau. Okay, this is h of tau d tau. Okay, now see, uh, we define now, hence we define we define now this part, okay, this part without e raised power st. Define now a transfer function, transfer function, function. What is the transfer function? First of all, the transfer function is, this is a transfer function. Transfer function. Transfer function of a system is equal to output divided by input. Transfer function of a system, please remember, it is equal to output by input. Now, what I have here from this equation, यहाँ पे मुझे क्या है? I have y of t, it is equal to e raised to power st, okay, e raised to power st, then minus infinity, integral minus infinity to plus infinity, h of tau e raised to power minus s tau d tau, okay. What is y of t? Y of t is my output. It is my output. What is e raised to power st? E raised to power st is my input. It is x of t. E raised to power st is my input. So this is input, or it is x of t. Okay. So if we, this is multiple to, entire integral h tau e raised to power minus h tau d tau. If I take it on the left hand side, then it will be divided. Okay. So what I will be having then, I'll be having y of t divided by e raised to power st will be equal to output divided by input will be equal to integral minus infinity to plus infinity h of tau e raised to power s tau d tau. Okay. So that is why I said, hence we define transfer function. What is the transfer function? H of s. So this is transfer function. Okay. Transfer function h of s. What is transfer function now from this equation equal to? It is equal to minus integral minus infinity plus infinity h of tau e raised to power minus s tau d tau. Okay? Please remember that this is a very important conclusion here, and I will call it equation 1. I'll call it equation 1. So this is the transfer function. And we can now write down, uh, we can write then y of t is the output. It is equal to, what is the transfer function of my system? H. H is the operator. Operator is nothing but transfer function. It is transfer function. Okay. So what is, I can write down then, my y of t will be equal to h times input. What is h times input? X of t. Okay, जो मैंने I think यहाँ लिखा था. Okay, यहाँ y of t is h times x of t. What is x of t? I can write down then y of t will be equal to h times e raised to power st, or I can write down this also, h of s times e raised to power st. Okay? Hence, the action of the system on an input e raised to power st is multiplication by the transfer function. अब देखिए इस सिस्टम में what is the output or the net result of this system? The action of the system that we have at the top, जो linear time invariant system है, इसका action क्या है? The action of the system is an input or on an input e raised to power st is multiplication by transfer function. I will just write it down here. Hence, we can note down that the action of the system on an input e raised to power st is nothing but multiplication by the transfer function. Okay, this will help us in deriving an important conclusion in coming discussions. So what is transfer function? H of s. Okay, h of s. Is it fine right now? Up till now, is it fine? अबरार बेटा आपको समझ में आया ये? कहीं क्वेश्चन तो नहीं है? अबरार is here. उज़मा बेटा अब ठीक है ये?
जी सर।
ओके, चलिए यही आप कह रहे थे इट शुड बी e raised to power minus s.
यस सर।
ओके, ठीक है। तो महविश को समझ में आया? महविश 65.
यस सर।
ओके, ऑल राइट. व्हाट अबाउट जुनैद 23?
Yes, sir.
ठीक है. Now please try to understand this thing. I'll just mention it. ये शायद आगे भी हम कहीं पढ़ेंगे. Please note it down. What is an eigenfunction? Eigenfunction and eigenfunction, there are two things basically. One is known as eigenfunction and another is known as eigenvalue. Eigenfunction in signals of systems, in signals and systems, is basically a signal that passes through a system without being multiplied or without being modified, except for multiplication by a scalar. So any function, any signal, if it passes through a system and it is not modified except the multiplication by a scalar, then that kind of function, it is known as eigenfunction in signals and systems. Okay, so we can then identify, we can assume then, hence we identify e raised to power st as an eigenfunction, we can identify then e raised to power st as an eigenfunction of linear time invariant system, because it is multiplied by some scalar, some term h of s only. Okay, and h of s correspond to eigenvalue. जो अब multiply इस signal को करेगा, that is known as eigenvalue. So it corresponding to eigenvalue. Okay, corresponding to eigenvalue. Now see, we can represent now this complex value transfer function h of s in polar form also. H of s is transfer function. It is transfer function, but a complex valued. In polar form, h of s can be represented as, in polar form, we can write down h of s as mod of h of s. That will give the magnitude. mod of h of s. Okay, then e raised power j theta. What is theta? Is the phase or angle of this function. So we can represent this in terms of mod of h of s, e raised power phi of s, e raised power phi of s, while mod of h of s, mod of h of s is nothing but it is magnitude. It is magnitude of the signal. Similarly, phi of s, phi of s is nothing but phase angle, phase angle of h of s, phase angle of h of s. Okay, therefore this is h of s only. ठीक है, हमने सिर्फ ट्रांसफर फंक्शन को we have changed it in the polar form. Therefore the entire signal, that is output of the signal, output of the system, y of t can be written as y of t is h of s into e raised power st. Okay, now since we have h of s in polar form, we can write it down in polar form. It will be mod of h of s e raised power j phi of s into e raised power st. Rizwan, is it fine? Rizwan बेटा ठीक है ये?
Yes, sir.
कोई क्वेश्चन तो नहीं है?
No, sir.
आसिम, आसिम को कोई सवाल तो नहीं है?
No, sir.
What about Burhan? Burhan is here? Burhan? Burhan is not here. Uh, Ubair? Ubair is here?
जी सर.
हाँ बेटा, आपको कोई सवाल तो नहीं है?
No, sir.
What about Hamad?
जी सर.
कोई सवाल तो नहीं है बेटा?
No, sir.
Okay, all right. ठीक है. Now see, this is what we have now obtained our output in polar form, okay, and with exponentials. Now we know that we have already used it. S is equal to, okay, S is equal to S, we have used somewhere S equal to sigma plus j omega, sigma plus j omega. Here S is equal to sigma plus j omega. Okay, we have already used it. We know now S is equal to sigma plus j omega. Sorry, it is sigma plus j omega. S is equal to sigma plus j omega. Okay, now we can use this S is equal to sigma plus j omega in this equation, and we will obtain y of t will be equal to instead of h of s, we will have h of s के बजाय होगा sigma plus j omega. Okay, sigma plus j omega, sigma plus j omega. Okay, what about this one? Rizwan will help me. Rizwan, what should I write down here?
E to power sigma plus j omega into t.
e to power e to power sigma.
Sigma plus j omega.
How is it sigma plus j omega?
S is equal to sigma plus j omega.
So j, then you have phi of this thing,
Sigma plus
sigma
j.
plus.
I
Okay,
was last term की मैं बात कर रहा था.
अच्छा, पहले लास्ट टर्म आपने पहले कहा था.
Yes,
चलिए
sir.
लास्ट टर्म. ओके, लास्ट टर्म. So e to the power sigma plus j omega
Omega multiplied by t, whole multiplied by t.
multiplied by t. Okay,
E to power j
then you have e to power j
phi of
phi of
sigma plus j omega.
sigma plus j omega, sigma plus j omega. Okay, ठीक है. All right. So if we will, अगर हम इसको let me continue it here. We can rearrange it. Uh, we can rearrange this. We can rearrange this. Just a second. Yeah, sigma there. Then you have 5. Okay, then you have st sigma t, and then you have this thing. Just a second. Am I doing it correctly? Okay. Mhm. So we can write it down like this: y of t will be equal to h of sigma plus j omega. This will be mod. Then you have e raised power sigma t will be one term. E to the power j omega t will be another term. Okay, and we can edit if we take j common. If we take j common, or let's not take j common. Let us not take j common. It will be equal to um, e j phi of sigma plus j omega. Okay, this is what it will be. If we'll finally reduce it in the form, rearrange the terms, it will be h of sigma plus j omega. This is what it will be. It will be e to the power sigma t, e to the power sigma t, then e to the power j omega plus phi of sigma plus j omega. Sigma plus j omega. This is j omega t here. Okay? J omega t plus phi of sigma plus j omega. This is what we will be obtaining. ठीक है, जब इसको rearrange करेंगे. And once we use Euler's formula here, will then obtain this thing. You have h of sigma plus j omega. Then we will have e raised power sigma t. Then e raised power j theta. E raised power j theta will be cos theta plus j sin theta. So we will first write down cos term, cos of theta. What is cos of theta? It will be omega t plus uh, phi of sigma plus j omega. So this will be omega t. Okay, this will be omega t. This is first term. फिर होगी j sin theta वाली term. j sin theta में भी आपको multiply होगा h of sigma plus j omega, and then you have e raised power sigma t here also, but then you will have j. So j will come out, j sin theta. Then you have sine of omega t plus phi into sigma plus j omega. So this is the final term. Okay, y of t will be equal to this thing. Y of t will be equal to this thing. Now we can conclude from this expression that the system changes the amplitude of the input. System changes the amplitude of the input. Now see, please try to analyze this equation. Output, जैसे input में हमारा input जो था, it had two parts. Okay, where is it? This is input. हमारी input में दो parts थी. So we used to have two parts in the input. One was real part, another was imaginary part. Okay. So it was e raised power st, e raised power sigma t times cos theta. Okay, cos omega t, whatever it was. Now here in the equation here, let me copy it here. मैं इस equation को copy करता हूँ. I can. So this was my equation. Copy. Okay, all right. Now see, if we see the input here, my output basically we can conclude from this equation. Output equation से हम ये conclude कर सकते हैं. The system changes the amplitude of the input by h of sigma plus j omega. Okay, if you can compare here, you have here e raised power sigma t. You have here e raised power sigma t. Then you have cos theta. You have cos theta. What is extra here is this term. Okay, extra term जो है ये असल में है क्या, ये एम्पलीट्यूड होता है. दिस इज द एक्स्ट्रा टर्म. अब देखिए साइन पार्ट में भी आपको यही टर्म एक्स्ट्रा है. ठीक है, एच ऑफ सिग्मा प्लस जे ओमेगा. So we can conclude here, in output, the system, okay, the system basically it modifies or changes the amplitude of the input signal by h of sigma plus j omega. because this is the extra term that you are finding in the output equation when you compare it with the input equation. Okay. The second thing you have to understand that the system also shifts the phase of the system. Okay, angle of the system. It also shifts the phase of the sinusoid components. What are sinusoidal components? You have sine theta and you have cos theta, sinusoidal components. Okay, sine theta somewhere here and cos theta somewhere here. अब देखिए, if you compare it with input, you have in input cos of omega t, लेकिन in your output you have cos of omega t plus theta. What is theta? Phi of sigma plus j omega. And in input you have sine of omega t, sine theta. Okay, then you have sine of omega t plus phi of sigma plus j omega. So that is the extra term. This is extra term. Okay, this much. In angle you will see that this is the extra term. So we can conclude that the system changes the amplitude of the input by h of sigma plus j omega and shifts the phase of the sinusoid components by phi of sigma plus j omega. Okay, I'll write down here. Hence, the system changes the amplitude. It changes the amplitude. I'll just conclude it and I'll stop. It changes the amplitude of the input signal by h of sigma plus j omega, and it also shifts the phase of sinusoid or sinusoidal components by phi of sigma plus j omega. Okay, and please remember that this system, linear time invariant system, it does not change the damping factor, which is sigma. Okay, sigma is known as damping factor. Sigma, S is equal to sigma plus j omega. Sigma is known as damping factor. So please remember that it does not change the damping factor of the system or the sinusoidal frequency of the input. Omega also is unchanged, or sinusoidal frequency of the input. Sinusoidal frequency omega of the input and damping factor sigma. ठीक है, ये दोनों चेंज नहीं होती है. किसी को कोई सवाल तो नहीं है? We will then next lecture में we will extend this discussion. Then we will try to find the Laplace transform representation. अभी मैंने Laplace transform representation नहीं की. ठीक है, I am just trying to analyze if I will apply a complex sinusoid to a system, what will happen. तो फिर हमने देखा इसमें क्या हो रहा था. We were able to deduce something that e raised to power st when it is applied to linear time invariant system, changes happen in amplitude and phase also. किसी को कोई सवाल तो नहीं है? अबरार यहाँ पे है? अबरार
यस सर, हेलो.
ठीक है बेटा.
यस
हाँ,
सर.
आपको कोई सवाल तो नहीं है?
जी नहीं सर.
नेक्स्ट क्लास कब है?
सर कल वेडनेसडे.
आज कब है नेक्स्ट क्लास? दूसरी क्लास कब है?
2 बजे.
2 बजे?
जी सर.
Should I stop now or I should continue?
नो सर, स्टॉप नाउ.
ओके, विल स्टॉप. मैंने वीडियोस अपलोड किए हैं. शायद मैं लेप्लास ट्रांसफॉर्म का भी वीडियो करूंगा अपलोड, जस्ट टू फिनिश द सिलेबस. तो आप उसको देखेंगे. जो मैं आई शेयर द वीडियोस. अगर किसी बच्चे को कोई सवाल होगा वो पूछ सकता है. बुशरा को समझ में आया ये?
जी सर.
I have not discussed Laplace transform representation yet. Please note it down. अभी मैंने properly ये खत्म नहीं किया. ठीक है. Although some of the terms have resemble to Laplace transform, but I have not concluded the discussion yet. अभी ये discussion conclude नहीं हुआ. Okay, I'll stop here.